Now we're going to do a script build example. Over the next few slides, we will build an increasingly complex script with more concepts introduced at each level. The scripts are attached to the PowerPoint for you to access and should be open in Notepad by default on Windows. Let's demonstrate opening a blank script in GMAT. If you just open GMAT, you'll be greeted here by this Welcome to GMAT window. We can close that. Go up to the left, top left, underneath File, hit the New Script button. You'll be greeted by a blank script in GMAT's script editor. Here's the Level 0 script. First, I'm showing the whole script after its completion in GMAT's full window. In the upper right-hand corner, you see the Mission Introduction script L0.script box highlighted in yellow. If you have the PowerPoint and you click that box, the script should open in Notepad. Another note, I just made up the levels, so level 0 will be the simplest, and we will add a level each time we add complexity. My objective here is to show you how to make something happen in as few lines as possible. This means we are relying on GMAT's default mission initializations for all of the resource settings. Now, let's look at the script. The shortest script I could come up with to move a spacecraft is to create a spacecraft, create a propagator, go to the mission sequence, and propagate. Line 1 creates a spacecraft ASAT, which is initialized with the orbital elements and epoch of the GMAT default mission. Line 2 changes the semi-major axis of ASAT from the default mission semi-major axis to 9,000 kilometers. The key point here is that the rest of the Keplerian orbital elements, such as the inclination, eccentricity, right ascension of the ascending node, etc., will remain that of the default mission. In line 4, we create a propagator resource, which is used to move the spacecraft position and velocity through time. We'll call this propagator aprop, again with all the default propagator settings. In line 6, we demonstrate a comet using the percent symbol. This is also shown in line 2. In line 7, the begin mission sequence command splits the script between the initialization section and the mission sequence. Finally, in line 9, we propagate our spacecraft from its initial state to its periapsis relative to Earth. To do this, we use the propagator resource aprop to propagate our spacecraft ASAT to the stopping condition of periapsis relative to Earth. Remember that parameters have dependencies. If our spacecraft is orbiting the Moon and we typed asat.periapsis as our stopping condition, GMAT would propagate to the point in the orbit where the satellite is closest to Earth, not the Moon. If we wanted to propagate to that point in the orbit where the spacecraft is closest to the Moon, we would need to propagate ASAT to asat.luna.periapsis, providing the dependency Luna. Again, it is important to know what the dependency of a parameter is, and when in doubt, to be specific. Now, let's run our script. We will hit Save, Sync, Run in our script editor. The mission script runs, and the mission run completed message will be written to the message window. The total runtime shows how long the script took to run. Obviously, there isn't a lot happening here, so the script runs pretty fast. Now, we don't have any information. GMAT didn't tell us anything. All it did was run the script, completed, and we didn't get any errors. In the next level, we'll add an orbit view to see what the spacecraft did during the run. Now let's run our level 0 script. Click Save, Sync, Run. The script window will disappear, and we'll see mission run completed. Let's spend a little bit of time talking about the default mission and the default settings in GMAT. The default mission includes a spacecraft called default sat, a default spacecraft, a force model, propagator, 2 visualizations, orbit view and ground track plot, a begin mission sequence command, and a propagate command with a 12,000 second end condition. If we create a resource without specifying details, the resource settings will be initialized to GMAT default. So that is what we did in level 0. We initialized the propagator to the default and then used it. Next, we'll take a closer look at the default spacecraft. What I've done here is open the default mission and save it as a script. When you double-click on the script, we will see the lines of code written here in the screenshot. Just a note, at the bottom you see an arrow pointing to line 27. The blue GMAT letters are automatically written when a line of code is written by GMAT. For example, if you make a change in the GUI editor and hit the floppy disk save icon, and then open your script, you'll see that a number of lines will likely have the blue GMAT lettering lines listed. Also, you'll see many more lines of code than your initial script had. Back to the script. We have opened the GMAT mission and saved it as a script. I made two changes to the default mission via the GUI. First, I changed the epoch format to UTC Gregorian, and second, I changed the state type to Keplerian. Now we can see the default mission's Keplerian elements on line 14 through 19. We can see an inclination of 12.85 degrees, shown in line 16, and a nearly circular eccentricity of 0.2, shown in line 15. In the level 0 script, we changed the semi-major axis, SMA, from the default 7,191 kilometers, shown in line 14, to 9,000 kilometers. But the rest of the elements were left as default and remain unchanged, which means our level 0 script, or spacecraft, has the Keplerian elements shown in line 15 through 19. Additionally, in the level 0 script, we did not assign a spacecraft epoch, so GMAT initialized the spacecraft epoch to the default, which is shown in line 11. The key point is that GMAT will initialize what it needs to default values if you have only defined a few fields. Now let's look at the default propagator. In the level 0 script, we created the propagator aprop and let GMAT initialize the settings to default. GMAT's default propagator has the default settings shown here. For many applications, these settings should be sufficient. However, if you're running a long simulation or maybe a simulation with multiple spacecraft, you may decide to reduce the accuracy requirements or increase the max step size to let GMAT run faster. The next thing to note is that in line 78, you can assign a force model to the propagator. GMAT uses the propagator resource to move a spacecraft along in time and space by integrating forces from the force model. The forces we can model are the central body, the gravity field of the central body, nth bodies such as Saturn or the Moon. And for low Earth orbits, atmospheric models are available for drag. Additionally, you can include solar radiation pressure. If the force model is not created and defined by you, then the propagator will use the default, which will look like this, which is an Earth-centered 4x4 gravity field with drag and solar radiation pressure turned off. Note again that in line 78, the force model is assigned to the propagator. GMAT's orbit view provides a 3D view of the spacecraft's orbit. Here, I am showing the default orbit view code created by GMAT. At a minimum, we need to provide lines 91, 97, and 98. Line 91 simply creates the resource and gives it a name. Line 97 adds resources in our mission to the orbit view. In this case, the default spacecraft and Earth are added to the view. If you had an interplanetary trajectory, you could add your spacecraft and multiple planets to an orbit view in a heliocentric coordinate system. Finally, in line 98, we need to give orbit view a coordinate system. In this case, a default coordinate system, Earth MJ 2000 equatorial, is used. GMAT always initializes this coordinate system, but you can use any coordinate system created in the initialization section in your orbit view. We'll cover more about coordinate systems on the next slide. Lines 106 through 111 define how the orbit view is oriented. These can be tricky to set up, so I want to point out that the user guide has diagrams, like the one shown here, along with definitions of vectors, points, and directions. This information should make setting up an orbit view go smoother. GMAT always initializes 4 coordinate systems, which are shown here in the mission resources tree. Earth MJ 2000 equatorial, Earth MJ 2000 ecliptic, and Earth fixed frame, and Earth ICRF. Search description of axes types in the user guide to see a detailed description of these and other coordinate systems. You can also define your own coordinate systems that are either centered on barycenters, celestial bodies, or spacecraft, and can be either inertial or rotating. We have now made it to level 1. In line 4, we're going to create a force model called AFM. We're still going to let GMAT default all of the subsequent force model settings. In reality, because we aren't changing any of the force model settings, the propagator is going to work exactly the same way as it did in level 0, but at least we've named our own. The next change we will make is in line 6, where we assign the force model AFM to our propagator APROP. When we ran level 0, we didn't have any output information from GMAT about the spacecraft's movement, so let's add an orbit view in as few lines as possible. Line 8, create an orbit view resource, which we will call OV. In line 9, we will add the Earth and our satellite ASAT to the orbit view resource. We also need to provide a coordinate system. We'll use one of the defaults, which is visible in the resources tree, Earth MJ2000 equatorial. Next, we'll push save sync run, and after GMAT completes the run, we will see the orbit view shown. The spacecraft starts at the top and moves counterclockwise to periapsis. Now let's run our level 1 script. Hit save sync run. We'll see the orbit view appear. We can animate the orbit view by pushing the animation play button. You can left click and rotate, and you can right click and zoom. To change a spacecraft orbit during a mission, you need to provide a change in velocity or delta V. GMAT allows both impulsive burns and finite burns. Impulsive burns provide delta V at an instant in time, and finite burns provide delta V over a period of time. Most users will understand this difference, but I make this point because performing an impulsive burn in GMAT uses the maneuver command, whereas performing a finite burn in GMAT requires the use of the begin finite burn and infinite burn block commands, along with a propagate command. But for now, let's look at an impulsive burn. The default impulsive burn uses the local velocity, normal, binormal coordinate system. This coordinate system is centered at the spacecraft and aligned with the instantaneous velocity direction, the orbit normal, and the binormal directions. The burn can be three-dimensional and is defined in kilometers per second. By default, the origin is Earth, so if your orbit takes you to another central body, change this accordingly. Note that you can define a burn in any default or user-defined coordinate system. Let's say we want to burn in the velocity direction. We could change the element 1 value from 0 to, say, 0.25 kilometers per second right here in line 95. We can also set a value for any DV element elsewhere in the initialization section or the mission sequence. We can also let GMAT solve for and assign DVs. More on this later. One simple way to output data from GMAT is to use the write command. The write command can write variables, arrays, strings, and resources to the message window or a report file. Shown are a few examples of write, sending data to the message window. Line 13 shows GMAT writing the resource chemical tank 1 with all of its fields to the message window, much like a structure in MATLAB. In line 15, sat.x and sat.vz will write the spacecraft position parameter x and the velocity parameter vz to the message window using the same write command statement. Line 17 demonstrates writing a string to the message window. Line 19 writes an entire array, while line 21 writes a single array element. Line 23 shows the creation of a string with the value of the x position parameter using sprintf, and line 24 shows the string being written to the message window with the script style, while line 26 shows the same string being written with the default style. There are a variety of styles and precisions that can be set when using the write command. And remember, you can also use the write command to write to a report file. For our level 2 script, let's add an impulsive burn. The first step is to create the impulsive burn resource, shown in line 8. We'll call this one DV1. You can look up in the user guide all of the options for an impulsive burn. Remember that by default, impulsive burns are set up in the VNB frame, or velocity, normal, binormal directions. This means that DV1 element 1 will be a velocity direction burn. Also note that the units for burns are in kilometers per second. In our mission sequence, we will keep the propagation to periapsis periapsis, and for comparison, we use the write command to write to the message window what the magnitude of the radius is at periapsis. The parameter rmag is the magnitude of the radius vector at the instant of evaluation. In line 21, we use the maneuver command to apply our impulsive burn to our spacecraft ASAT. In line 23, we'll propagate ASAT to apoapsis, following similar syntax to line 18. In line 24, we'll ask GMAT to write the magnitude of the radius now that we are at apoapsis after having performed a 0.1 kilometer per second maneuver. You can see in the message window that the periapsis radius was 8,771 kilometers, and at apoapsis, the radius is 9,792 kilometers. Based on our knowledge of the default orbit, we know we have successfully raised apoapsis. We can also visually see the changes in our orbit view window. Now let's run our level 2 script. We'll hit save sync run. The orbit view appears. In the message window, we see running mission. We see our first write, our second write, and our mission run completed. Now we can animate our orbit view, and we see the orbit go around and then diverge from the original orbit, which means our delta V was applied. In level 2, we have defined a DV to apply to a spacecraft. Next, we will solve for a DV to change the orbit using a target control sequence powered by a differential corrector. A differential corrector is simply a numerical solver that solves a boundary value problem. There are several available within GMAT. You are probably familiar with the Newton-Raphson method. Additionally, Broyden and modified Broyden are available and offer slightly different computational characteristics. GMAT uses the differential corrector to solve a target control sequence. The minimum we need to do is create the resource, like in line 92. We can change which numerical technique we use by changing the algorithm field. We can also adjust whether to use a forward, backward, or central differencing method. Depending on your problem and the initial guess, adjusting these settings may help provide better stability or reduce the number of iterations needed to solve. A target control sequence, or targeting loop, consists of a minimum of 4 commands: target, vary, achieve, and end target. Additionally, a target control sequence requires the use of a differential corrector resource. The vary command tells GMAT what it can vary, and the achieve command provides the goal of the targeting loop. In the first example in the upper left, we use the targeter to find the root of the function shown in line 8. In line 7, we use the vary command to tell GMAT to vary x and to start with an initial guess of x equals 5. In line 9, we use the achieve command to tell GMAT to compare the value of y with our goal of y equals 0. We also provide the tolerance that we want the target control sequence to use as a stopping condition. The target control sequence uses the differential corrector in an iterative loop to solve for x, such that the y equals 0 with the tolerance shown of y equals 0 in the tolerance brackets is achieved. In the lower example, we use a target control sequence to raise the apoapsis of the default orbit to 42,164 kilometers. In lines 1 through 4, we create a spacecraft, propagator, impulsive burn, and differential corrector, allowing GMAT to initialize all of these resources to their defaults. In the mission sequence, we start the target control sequence in line 8. There are some additional options set in the curly braces, which we will not cover here. The vary command in line 10 sets up the initial guess for aburn.element1, equal to 1 kilometer per second. We also see some more options about how the differential corrector will solve for subsequent iteration values. The perturbation is the step size used to calculate the finite difference derivative. The fields lower and upper define the limits of aburn.element1. We can also set max step sizes for the variation of aburn.element1. However, in this instance, we don't need to. In line 13, the maneuver is performed with the vary command's most recent iteration for the value of aburn.element1. Then, in line 15, the propagator propagates the mission forward to apoapsis. In line 17, the target control sequence checks to see if the magnitude of the radius of the spacecraft at apoapsis is equal to the desired value within the tolerance provided. The target control sequence will repeat with a new guess for A burned at element 1 until either the achieve command is satisfied or the maximum iterations allowed for the differential corrector is reached. For level 3, we will incorporate the differential corrector and target control sequence into our script. Let's say we want GMAT to raise the SMA of ASAT from the initialized value of 9,000 kilometers in line 2 to 9,500 kilometers. We know to do that we'll need to apply a delta V, so let's utilize a targeting loop with a differential corrector to raise the SMA to 9,500 kilometers. First off, I have removed the dv1 element 1 equals 0.1 from line 9. We will let the differential corrector figure out the magnitude of the delta V. But note that all three elements of dv1 will be initialized to 0. Next, in line 10, we create the differential corrector, which we'll call DC for short, and let GMAT default all of the settings. Now we move to the mission sequence. Note here, I also remove the write commands for simplicity. Instead, we'll check to see what happened with the orbit view. We want the maneuver to happen at periapsis, so we leave the propagate in line 19. Now we add the target control sequence in line 21. First, we need to add the target and end target block statements. For the target command, we have to tell GMAT which differential corrector to use, in this case DC. The vary command tells the differential corrector what it is going to vary, in this case dv1 element 1, which was initialized to 0 in the initialization section. We're going to provide an initial guess of 0 kilometers per second and see what the corrector does. So now the targeting loop knows that it is going to use the differential corrector to vary dv1 element 1. Next, GMAT applies the maneuver dv1 to ASAT and the propagator propagates to apoapsis. In line 25, the achieve command tells GMAT that it is varying dv1 element 1 in order to achieve SMA equals 9,500. So now the differential corrector can vary dv1 element 1 until SMA is within the tolerance of that target. We need to place the achieve command in the mission sequence where we want to achieve our semi-major axis value. So in this case, we want our SMA to be 9,500 kilometers after the maneuver dv1. If we place the achieve command before the maneuver command, the target loop would fail because there is no way to achieve a change in SMA without the maneuver being applied. Now we end the target block and press save sync run. After the run completes, we see the orbit view shown here. Prior to the target control sequence, the spacecraft was at periapsis, and GMAT figured out how to change the orbit via a maneuver to raise the SMA to 9,500 kilometers. So that is what we see here. The orbit visually changes, and ASAT has been propagated to apoapsis. Now let's take a look at the message window. The first bolded arrow shows what happened when we provided an initial guess of 0. GMAT ran the targeting loop and found that the SMA after the 0 kilometer per second maneuver is 8,999.9 kilometers. On the next iteration, the differential corrector calculates a positive value for dv1 element 1 equal to 0.18 kilometers per second, and then calculates an SMA of 9,536 kilometers after the maneuver. The differential corrector now continues to step through the assigned numerical method and develops a better third iteration guess and gets much closer. On the final iteration, the semi-major axis achieved is within the tolerance we requested, and GMAT reports out the final value of dv1 element 1. Now let's run our level 3 script with our targeter. We'll hit save sync run. We see the solver window appear, the orbit view appear, as well as our iterations shown in the message window. So we can see that the solver converged on a 9,500 kilometers semi-major axis. We can look in the message window and see the what it achieved each time as it was going through and sizing the delta V. Finally, we can look at our orbit view and animate it. Thank you for watching. We hope this has been helpful. This completes our first 3 levels of scripting. We'll continue more in the coming weeks and months.